So, we will continue our discussion on the interaction of charged particle with electromagnetic field in the quantum picture and in relativistic case. Essentially, this is what we call quantum electrodynamics, but we will come to the formal quantum electrodynamics as a field, quantum field theory at a little stage, but this is basically to build or give way to such a quantum field theory, how to think about that. Okay, so today, we will consider the discussion that we have been doing in the past couple of lectures forward. So, we were discussing the gauge freedom associated with the 4 vector potential picture of the electromagnetic field. So, we said we could express the electromagnetic potential A mu or express the electromagnetic field in terms of the scalar potential and the vector 3 vector potential, putting them together as components of a 4 vector. We can consider A mu, the 4 vector, as the 4 vector potential representing the electromagnetic field. And we said if we consider the measurable quantities electric and magnetic field E and B associated with this A mu, then we will see that the A is not uniquely defined or fixed. We can actually take A mu to A mu plus derivative of some scalar function chi, which will still give you the same electric and magnetic field. And this freedom to choose any A mu related by this relation is basically called gauge freedom, and that is a kind of an arbitrariness in defining the potential, but it is taken as an advantage in quantum electrodynamics. We will come to that a little later when we discuss the gauge symmetry. But at the moment, this lets us fix the A mu so that dou mu A mu is equal to 0. That is, A mu can be made divergence-less, for divergence is equal to 0 by appropriately choosing the scalar function chi. Now, this is what we saw yesterday, and even after fixing this, there still we can actually transform A mu to A mu plus dou mu lambda. This second A mu is the new A mu now, A mu that satisfies the. So, let me call this A mu prime to avoid any confusion. So, A mu prime is the new field, and A mu prime can be transferred now to A mu prime plus some dou mu lambda, and then of course, this should also give you the same electric and magnetic field, because it is similar to the earlier transformation. But we have to check whether the condition, the divergence-less condition of A prime mu is also conserved. If you take the divergence of the new field A double prime mu, then we will have divergence of A prime mu plus dou mu of lambda. So, this first term is equal to 0 and second term can be made 0 if we choose lambda appropriately. So, this is equal to 0 for particular lambda. So, first one transformation fixes the fixes a mu, so that it is divergenceless, and then we see that still there is a freedom to choose the potential, and we see that there is always it is always possible to choose a double prime by adding a derivative term of a scalar function again to the A prime, as in the case of equation 2. This will not change anything, it will not change electric and magnetic field, the physical quantities, neither will it change the condition that the A prime is divergenceless, or therefore A double prime is also divergenceless if lambda satisfies the condition that dou mu lambda is equal to 0. So, the second transformation is not for any scalar function, unlike the first transformation where chi could have been any scalar function. Lambda is not any scalar function, lambda is the scalar function which satisfies the condition dou mu is equal to 0. So, that is basically the thing. We will return back to this when we discuss explicit expression for A mu later. Now, this actually says E is equal to minus del phi minus dou A over dou t, and B equal to curl of A as satisfied by A mu or A prime mu, which is essentially equal to A mu plus dou mu chi any scalar function chi, and A double prime mu, which is A prime mu plus dou mu lambda, where lambda is a scalar function. So, that dou mu lambda is equal to 0, and this gives dou mu A prime mu is equal to 0, and also dou mu A double prime mu equal to 0, divergence. So, we have the same physical situation for any of these fields, and then in A double prime we will see that A double prime mu we have fixed the arbitrariness. So, that is unique in the sense that that is unique in the sense that you cannot add any more terms in that thing, because lambda is already the choices of chi and lambda will fix this thing, or the condition for A mu prime divergenceless A mu prime is satisfied here. Let us look at the Maxwell's equation with all these conditions applied to the potential. Maxwell's equation written in terms of the potential was dou nu A mu minus dou nu A nu for divergence equal to J mu. So, if we have the condition that gauge choice is such that dou nu is equal to 0, as we discussed in the earlier case, this condition is called Lorentz gauge condition. In that case, the second term from the Maxwell's equation drops out, and then we have dou nu A mu equal to J mu, or in a slightly more compact way we can write it as box square, which is equivalent to dou nu or dou mu, where nu is summed over, and in that case I can write the box square A mu equal to J mu, slightly neater way of writing it, meaning the same thing in any case. Now, let us come to solutions of this equation. Okay. This is the Maxwell's equation with Lorentz gauge condition applied. Maybe I should highlight this. Okay. So, this is our Maxwell's equation with Lorentz condition. So, let us look at it. So, we have del square A mu equal to J mu equal to 0 for free electromagnetic waves, or I would say in the quantum picture free photons. We are not quantized it yet, but let us say that we can do that and then think about the electromagnetic field as a collection of photons. In that case, A mu represent the photon. Now, we are actually deviating a little away from the earlier interpretation or earlier picture of giving more physical meaning to the electric field and the magnetic field, and then considering the potential as an auxiliary function. Okay. That was the earlier picture, and then we said that we can actually have different potentials even, which will give you the same physical situation. Now, in the quantum electrodynamics, we will deviate from this picture and then say that photon, which is the quantum of the electromagnetic field, is more meaningful physically, and the field associated with that is the potential is equivalent to the potential A mu, and therefore, A mu is the one which represents the photon. Associated to that any photon, we can actually think about the electric field and the magnetic field. When you come down to or find see the picture of the photon in the non-relativistic case, we will see the electric field and magnetic field associated with the photons in that way, with certain relations between them. But A mu therefore takes more physical meaning in quantum electrodynamics, and arbitrariness can be fixed by choosing the gauge conditions, and then it is somewhat uniquely fixes the potential corresponding to the or the potential corresponding to the photon or the wave function corresponding to the photon or the field corresponding to the function. At this moment, I will be a little vague in defining what is wave function, what is the field, what is the potential, etc. Basically, I will interchange call A mu sometimes as field, sometimes as the wave function corresponding to the photon, sometimes as the potential. So, all these are the same thing, but looking at from different pictures. Accordingly, the interpretation is slightly different, but basically it is the same entity. So, for the time being, we will not distinguish it clearly. As we come to the clear representation of the quantum field corresponding to the photon, we will as an operator, that is the correct picture in quantum field theory or quantum electrodynamics, we will talk a little more about what is the quantum field A mu. but essentially that is the same as the potential that we are considering in relativistic electrodynamics. So, this the box square is essentially called D'Alembert. So, D'Alembert A mu acting on D'Alembert is an operator which acts on A mu here to give you 0 for free photons. Solution? Well, this is basically a easy guess. If I take A mu to be some constant function, constant 4 vector as far as x is concerned. D'Alembert is an operator which acts on the coordinates, not on the momentum. So, I can take for some constant function in a constant in x, a function which is constant in x, but could depend on momentum, a 4 vector, and explicit coordinate dependence in an oscillatory exponential minus I q dot x, where q dot x is a 4 vector dot product q mu x mu, where mu is summed over. Okay, let me convince you that it is actually indeed a solution, or what are the conditions that anything should satisfy for this to be a solution. So, let me act on it by nu dou nu A mu is equal to dou nu acting on epsilon mu q e power minus I q dot x, okay, which is equal to dou by dou x nu acting on the same thing, epsilon mu q e power minus I q 0 t minus q 1 x minus q 2 y minus q 3 z. Okay. So, now let us take case by case nu equal to 0, which is dou by dou t of A mu, which is equal to dou by dou t of epsilon mu q e power minus I q 0 t, rest of it is 3 momentum dot product with 3 coordinate x mu, x vector. So, there is only one particular place where t appears on the right hand side, it is exponential minus I q 0 t. So, when I take the derivative, epsilon mu q is independent of t, comes out e power minus I q 0 t, okay, is minus, when the derivative acts on it, minus I q 0 e power minus I q 0 t, and other things remain the same, minus q dot x. So, this is essentially equal to minus I q 0 A mu, all right. So, now similarly dou by dou x A mu is equal to dou by dou x epsilon mu q exponential minus I q 0 t minus q 1 x q 2 x y minus q 3 z. So, that will give you minus of minus plus I q 1 a. So, that is one thing. Now, what we want to have is dou nu acting on mu, which is equal to dou square by dou t square acting on mu minus dou square by dou x square acting on mu minus dou square by dou y square acting on mu minus dou square over dou z square acting on mu, same mu. And we had dou by dou t mu is equal to minus I q 0 mu. So, dou square mu by dou t square is equal to minus I q 0 independent of t and dou by dou t acting on mu, which is another q 0 minus I q 0 mu, which is equal to minus q 0 square mu. And dou square by dou x square mu will give you minus q 1 square mu, and dou square by dou y square mu is minus q 2 square mu, and dou square over dou z square mu is equal to minus q 3 square mu. Putting it together, dou nu mu is equal to minus q 0 square plus q 1 square plus q 2 square plus q 3 square, which is equal to minus 4 vector square q square mu. And we have Maxwell's equation with Lorentz gauge condition, del square the box square mu equal to 0, and that gives us minus q square mu equal to 0. We essentially q square need to be equal to 0. And what is q square? Q square is equal to q 0 square, which is essentially e square minus p square or 3 vector minus 3 vector square, which is equal to m square c square. And when we say q square equal to 0, m square is equal to 0, q square for vector square is equal to 0. Now, as we said earlier, when we consider the mu as representing the photon and we associated a form momentum q with mu, like in this case mu is equal to epsilon mu q exponential minus I q dot x is what we considered, right. So, q is essentially then interpreted as the momentum, form momentum of the photon, and Maxwell's equation gave us form momentum square is equal to 0 for the photon. Of course, you can ask the question, like this was in the case of mu satisfying the Lorentz condition. What about if I consider mu which is not divergenceless? Then still can I interpret this as the photon with mass equal to 0. So, this essentially gives you massless photon. Actually, I mean, when I say massless photon, in the sense it says that photon has no mass. But then you remember, this gauge condition is not an additional condition that we can apply. We could have applied the gauge condition and chosen any condition, any conditions that satisfies the gauge transformation, so that electric field and magnetic field remains the same. So, from that point of view, the physics should not depend on whether I have taken Lorentz gauge or not, Lorentz gauge condition or not, which means the A mu that satisfies the Maxwell's equation the way we had written with the gauge condition, or some A prime which is not divergenceless and do not satisfies the Lorentz gauge condition, but is derived related to this A mu through a gauge condition, gauge transformation, by adding a or differ by a dou mu chi kind of a term, where chi is a scalar field. In that case, they are physically the same, equivalent to each other, and therefore, all of those when we consider as photons, if in one case it is massless, then in all other cases also it should be massless. So, this represents the same this thing, and then photon in any case, whether there is a Lorentz condition applied or not, it is massless. Only that when you take it in this fashion, it is manifestly clear, it is manifestly there, it is very apparently there, clearly there. Okay. Now, let me look at it a little more and then see what is the interpretation that we can give to epsilon. So, we had the solution f A mu equal to epsilon mu q e power minus I q dot x for the photon field satisfying the Maxwell's equation. Let me write this epsilon mu as epsilon 0 and 3 vector epsilon e power minus I q x. So, I have not explicitly written the q dependence on the epsilon now, it is understood that it depends on q. It is just for the sake of clarity that we are not adding the bracket with q there. What is E? Electric field is equal to minus grad phi minus dou A by dou t. Supposing we do not have any electrostatic potential phi and electric field is only due to the changing magnetic field, like in the case of electromagnetic waves. So, for a free photon, we can imagine that there is nothing else but a changing electric field and changing magnetic field, one inducing the other. So, in that case, this is equal to 0. So, you have minus dou A by dou t as the electric field, and that is essentially epsilon exponential dou by dou t acting on this thing will give you minus I q 0 e power minus I q x, or minus I q naught epsilon which depends on q exponential minus I q naught t exponential I q dot. So, this is basically the electric field with explicit dependence on the time and x written. We are familiar with this, and the amplitude is given by a complex amplitude here minus I q naught epsilon 3 vector. direction of the electric field is the same as the direction of the epsilon 3 vector. And therefore, we can say that polarization direction is of the photon is that of the epsilon. Now, let us see what happens to the polarization vector in the case of Lorentz condition. Let us look at Lorentz condition, which is dou mu A mu equal to 0. A mu equal to epsilon mu e power minus I q x will immediately give you q mu or minus I q mu epsilon mu is equal to 0 when taking when dou mu is acted on A mu. So, this says that Lorentz condition says not all the components epsilon 0, 1, 2, 3 are independent of each other, but depends through the relation q mu epsilon mu equal to 0 or q naught epsilon naught minus q 1 minus q 1 epsilon 1 minus q 2 epsilon 2 minus q 3 epsilon 3 equal to 0. So, for a fixed q epsilon, all the 4 components of epsilon are not independent of each other. So, there is a relation that they had to satisfy, therefore, there are only 3 independent, that gives 3 independent components. Further, we can choose lambda. Let us choose lambda equal to I A exponential minus I q dot x. What is dou mu lambda? Dou mu lambda is equal to I A minus I q mu e power minus I q dot x, and dou mu lambda is equal to I A minus q square e power minus I q dot x. But q square is equal to 0 says that this is equal to 0. So, an A scalar function satisfying dou mu lambda equal to 0 is I A exponential minus I q dot x. Well, this I A is kept like that because of reason that will be clear just now. So, this is 0 because q square is equal to 0. So, now what does that tell you in terms of the change in epsilon corresponding to a change, a transformation of A mu to A mu plus dou mu lambda, which is equal to A mu plus A q. So, we had I A minus I q mu exponential minus I q x. So, if I write A mu as epsilon mu e power minus I q dot x, then minus plus I A times minus I q mu is plus A q mu exponential minus I q x, which is epsilon mu plus A q mu e power minus I q x. If I denote this by some epsilon prime e power minus I q x, As A mu goes to A prime mu equal to A mu plus dou mu lambda with this particular lambda, this gives epsilon mu going to epsilon prime mu, which is equal to epsilon mu plus A q mu, right. Fine. So, I have epsilon prime mu equal to epsilon mu plus A q mu. Now, I can choose A so that epsilon prime mu, the 0 is equal to 0, all right. So, this is why we had taken the lambda in that particular way. So, I can choose this. So, initially we had a condition on epsilon, that epsilon 0, q 0, epsilon q 1 epsilon 1, q 2 epsilon 2, q 3 epsilon 3 equal to 0. Now, that epsilon prime, okay, so this is applicable to epsilon prime as well, because it is the same this thing satisfying same condition, Lorentz condition. This is basically the Lorentz condition, and changing it by lambda, which has dou mu is equal to dou mu lambda equal to 0, will not change the Lorentz condition. So, this actually tells you that q 0 epsilon prime 0 minus, let me write it as q dot epsilon prime is equal to 0. Since epsilon prime 0 is set to 0 by appropriately choosing A, we have q dot epsilon prime 3 vector is equal to 0. Epsilon 3 prime has 3 components, but then there is a condition q dot epsilon 3 vector prime is equal to 0. So, essentially there is a relation between these 3 components, and therefore, that gives you 2 independent components. Or we can say that photon has 2 degrees of freedom. So, let us summarize what we have been doing. We had the Maxwell's equation in terms of field tensor, F nu is equal to J nu, dou mu F mu nu equal to J nu, and we could write F mu nu in terms of vector potential as dou mu A nu minus dou nu A mu. That gave the Maxwell's equation as dou mu A nu minus dou mu A mu equal to J nu. Then we had the Lorentz gauge condition, dou mu A mu equal to 0. This Lorentz gauge condition will not affect physics, because we can find out an A mu which satisfies the gauge condition with the same electric and magnetic fields associated with it as in the original case, and that gives us Maxwell's equation del square the box square A mu equal to J mu. Then we considered the solutions, A mu equal to epsilon mu q exponential minus I q x for j equal to 0 case, which is then interpreted as the representing the free photon without any charge density or current density in the region. Isolated electromagnetic wave freely propagating in the quantum picture equivalent to a photon represented by A mu. And that told us that we have q square equal to 0, massless photon, and epsilon mu is essentially the polarization vector in the 4-dimensional case, and especially in the 3-dimensional case, it is the familiar polarization associated with electromagnetic field. And we saw that it has 2 degrees of freedom or 2 independent components. Okay. Maybe I should write it in that fashion. So, this with the Lorentz condition, this has 2 independent components. That in turn tells us that photon has 2 degrees of freedom. So, we will come to the discussion of the interaction of the charged particle with such photons, photon fields in the coming discussion.